Okay, so the mu operator is the minimization operator. That's why they're separated, because the whole thing is called the mu calculus, but the mu is actually the minimization. We just use mu alone. So he is asking for the last two. Computable function, so primitive recursion is the easier one though. That's the one I understand better too. Let's see, so we can start with that. Right, so I guess back to 23. Did people have any questions on projection or induction? Or the projection or composition?
Can you explain composition?
Or even the base cases, actually. Anyone have questions on the base cases? Those are...
Everything else kind of makes sense.
Yep. So, which one? Composition?
Okay.
Okay, scan the block of... Yes. Okay. Assume H is the composition of F with K array functions, G1 through Gm. We start in the state. Composition of F with K array functions. Multiple K array functions? Interesting. So composition should just be one call of G. So we start by duplicating the entire list of arguments. Fine. We then position the read head at the B before the right hand copy of the arguments. And run, so he has a blank, I guess, between the two. And run the G1 program resulting in this. You know, duplicate arguments ending with the read head before the right hand copy of the arguments, so run G2. Until we've computed all the G's, then we compute F on the G's. So, it's a little confusing just because he's reversed his notation. Notice that he's composing F on a bunch of G's, not the other way around. Remember in the previous lecture, hey, come on in guys. So here, steal this chair, and eat some brownies. So yeah, that's probably the most confusing part of this argument, is that if you look at his composition definition from lecture 22, and you look at then his composition induction case, he has swapped F and G, right? Because in 22 he uses a single function G composed on a bunch of functions F1 through stuff, right? Is that correct? Someone looking at 22?
Mm-hmm.
Yeah. And here he's done exactly the opposite. So that could throw you off a little bit at first. What is he doing? Okay, once that's clear, how does this case work? Well, all he's doing is he's preserving his original input, which is necessary because it's necessary because he's going to need to keep recopying it, right? So he preserves his original input, then he copies it, and he computes G1 on that copy, right? Then he goes back to the beginning, copies his input to the right of his G1, and then computes G2 on that. Does that make sense? Does anyone have any? I could draw some stuff if that would help people, but does anyone?
So he just keeps duplicating them, and then until we run out of G's.
Yes, until we've computed G1 through Gm, each member of G1 through Gm once on one of the copies of the input. So then on our tape we'll have the original input and G1 of the input, G2 of the input, etc. onto Gm of the input. Then he computes F on G1 through Gm of the input. Is it actually including the original input? I don't think so. Function composition should just take in, probably ignores the beginning of it.
Yeah,
Yeah,
he says
it
erase our original argument.
Oh, that makes sense.
Yes. You will only erase the original argument once you know you've made all the copies that you needed to compute G. and then you're computing F on the copies. So
Okay,
that's-
that makes perfect sense. Okay, cool.
Fortunately, these are like fairly high level, which means you're allowed to be fairly high level in your proofs. You can like just explicitly give the Turing machine that would do that. It's just gonna take you a while. Like think about this argument in terms of actual transition functions. You've got to be like counting the number of blanks every time you scan left
It's
to
like the
know
last
when you're at
homework.
the input. What?
So it's like the last homework kind of.
Yeah, we actually we ended up. I'll talk about the grading of that after this. Needless to say, it ended up being pretty lenient. But let's see. Right. So back to this. Did anybody else have any questions on what we already have?
Were we sort of, I don't know, we had a question on the minimization definition? I don't know. If that's,
Yeah. Minimization is the confusing one.
yeah, mostly, yeah, especially just on the notation, especially as it pertains to the homework, because, so, is the, like, MUI dot F just trying to indicate that that's, like, the least, is G equal to the least I, or is it equal to F evaluated on the, well, I guess F evaluated on the least I is 0. We were sort of confused on how that works, especially like how it works with, like, how, like, that works with the analogy with the while loop.
Sorry, can you say that again?
Because like he sort of makes an analogy between, so he says that like primitive recursion is like a for loop, which made sense to us, but the like saying that minimization was sort of like a while loop I didn't entirely get. I couldn't entirely
Yes.
see that.
So G of x equals mu I. So mu is a function, right? And it's on I, and so you're saying the least I such that it's a while loop because it goes and computes FJ is defined for blah is also computable. So let's see, if F is then G of x equals UI. What is G is defined by minimization?
Also, what does the dot mean there?
Yeah, the notation.
Is that like lambda calculus
Challenge.
notation with like apply or something?
Sorry, give me one moment. So you were saying this is like a for loop?
Yeah, that's, he had in that last paragraph he says that like
Mm-hmm.
the primitive recursion is a kind of for loop and minimization is more like a while loop.
So I think what it's doing, and you guys have more context than I do actually from the. Oh right, he says it down here.
Yeah.
Yes. So basically, I think what's happening is you are utilizing the previous definition, right? You are. This is gonna be some like primitive recursion going on here. But where the least I such that is defined.
And F of I is 0.
Yep.
We didn't define f to take.
So
like
basically what it does is it does primitive recursion until you hit an I such that this would equal 0. Right?
And then we also
So I believe you stop at the one before this, right? Because fi of this, where this means the least I such that this is defined for all j less than I and this equals 0. So you're talking about going until this this equals 0 and then you're left with this. Does that seem accurate?
yeah, so I guess you would start at 0 and keep increasing until you
Yes.
found one that fit.
Right.
Okay.
What is the MUI dot F? Is that like a new sentence or is that what's going on there?
That is a fantastic question.
My impression is that it's saying that G is equal to the least I. It's not equal to F value. It's like like the value of that function is I.
So it's like least I such that F.
Yeah. So like say the least I was 2, then G of x1 xn would equal 2.
I see.
I think.
Oh yeah.
Is my impression? Because F of I is equal to 0, so presumably the value of F is sort of useless.
Well, the value of f just kind of tells you what the I is, right?
Yes,
Like
yeah.
helps you get there.
Yes.
But like f of I at that thing is 0,
Mhm.
so like.
I think the important thing is what we were just talking about, though. The important takeaway is disability. So, mu I equals this, and this. And is the G computable? That's my question, and I think the answer is not necessarily. Right?
What G and. Well, isn't it half? Isn't that what the.
F is computable.
Yeah, I was gonna say.
Each occurrence of F is computable,
Mhm.
but the while loop seems to be able to run forever, which isn't necessarily a bad thing because Turing machines can run forever.
Mhm.
So the idea that this might not halt isn't necessarily bad. It's just something important to note.
But isn't that so? Like maybe I'm misreading a sentence, but like
Mhm.
that bullet point says like then G blah 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 is also mu computable. Isn't it saying that like G is mu computable if every F is mu computable?
These are not the same F and G, right? Because notice this is an n+1 array function. This is an n array function. The F and G change bullet
Oh
point
yeah,
to bullet point, right?
but like in the last bullet point, isn't the G that we define there as the minimization, like G defined by minimization is
Also
mu computable? I agree that it can run forever, but it seems like this is saying that G is mu computable.
Where does it say that? Because all I'm reading is if F is an n+ array mu computable function,
Then G.
Then G dot
At-
dot whatever
at-
at the end of the line
at
says
the end of-
is also mu computable.
oh, you're right. Yes. Okay. Yeah. This is a little always hold. Good. Yeah. Then G would be mu computable because right you can just compute this. So the way you compute G. So what we're going to need to do for the minimization proof, right, is to compute G, and the way you compute G is by running F.
Mm-hmm.
On like 0 up until it hits some 0, right?
What if it doesn't hit some 0?
Then
Can you guarantee that either, or like would the other situation?
does that mean then
like the J
well,
plus the I definition?
let's see. So F is mu computable. It's also what does mu computable mean? It's always gonna halt.
We didn't really get an exact definition of what that meant.
Recovering the definable function. Right, that's
This is defining what mu computable is.
let's think about that for a sec. I'm gonna look something up because is mu computable intuitively to me says it always halts.
Well, I think it has to because like based on the next theorem, if it's Turing machine computable and Turing machine computable and mu computable are the
Yeah,
same thing,
so-
it has to.
Right. But why does F? Why will F of I for some I equals 0? I greater than 0 equals 0. Actually, even at 0 doesn't necessarily equal 0 because it equals whatever it equals at the base, which isn't necessarily 0.
Can
In fact,
guarantee that
0
either
stops
this one
immediately.
or this one breaks.
Right. So note here is something imprecise flaw. There's a bit of
Is it not defined?
total.
What does it mean to be not defined? Or is it measure value?
Okay, so I think it's this last sentence, the second last sentence here. It's pretty important, right? Here he is doing what I'm doing, which is calling out minimization for having potential issues, right? So let me remind myself of what a total function is versus. Does anyone remember offhand? I'm not the best with terminological stuff. Total function. When's the last time I did that? Computable function. Right. Okay. So total is more what I'm actually thinking about for computable, and minimization can diverge. So mu computable doesn't appear to be using mu computable the way I would use the word computable, right? Because then he admits that if you build something with minimization, it may diverge.
Okay, so it's
So you just need to mimic the mu computability.
okay, so
The Turing machine not halting isn't necessarily an issue.
so it can just run on.
Yes. I'm gonna eat some brownie. Right, okay. Go back to the homework. Did that clear up minimization for people? Or do people still have questions about minimization? So maybe I should rehash that now that, because that was going on for some time. Right, so what is minimization doing? You're trying to compute the least I such that you can kind of do this whole primitive recursion thing. You can compute f at 0 and then f at 1 and 2, but then at 3, if it equals 0, that's where you stop, right? And you output how many times you did the primitive recursion, essentially, right? That's what G is doing. It's outputting how many times you do this recursion before you halt. However, f is mu computable, but that doesn't guarantee that even if f is total, then even if f is total and you can always halt on f, you don't necessarily halt on G, right? And the weird thing is f itself might not be total because if it's defined via minimization, you also might not halt on f. Right?
What is the line there in the definition of minimization saying that it's defined for all j? How could it not be defined? Like, can you have a mu computable function that just doesn't, like, the number is too big for it?
Where?
In that last bullet point,
it
in the
says
bullet point for
The
minimization.
least I such that f of j xi to xn is defined for all j less than I.
Yes.
Is it like possible to, or like is it like does it make sense for there to be a number theoretic function that doesn't work for some j? Like does it like has a hole somewhere in the middle? You know, like it works for 0, 1, 2, doesn't work for 3, it works for 4 onwards.
Where does it say that where means the least I is defined for all j? Well, think about let's see. If it's not defined, what is it doing? It's just like
I don't know what your like function would it just not return, or that's still technically possibly mu computable? Does it just like break?
I'm not totally sure. Fortunately, I don't think it matters for the homework problem at the very
Well,
least.
couldn't your while loop terminate on a place where it's not defined?
Yeah, it could break on either if it's 0 or if it's not defined. I guess if you just can't compute, but then it breaks.
But I don't know what the notion of not
But
being defined is.
But f is also computable, which would imply that Turing machines can compute it.
Not defined. It's a very good question. I think I'll talk to the other TAs about that actually, because I'm not 100% sure. I don't think you have to worry about it, honestly.
Alright.
Let's for now discuss as if they're all nothing's ever undefined.
Okay.
I think that's inaccurate, but I'm not 100% sure how to deal with it, and I don't want to waste too much time on it. So I'll make a Piazza post.
Okay.
I'll make it either way. So like even if you don't have to worry about when it's not defined, I'll like explicitly say so. Feel free to poke me if you haven't heard anything like an hour after this, but I should post something up before I post the video. Right. Okay. So let's ignore that. Other than that issue, is minimization clear?
Yeah.
Yeah.
Okay. Cool. Back to the inductions. So, oh, that's not what I wanted. What are these going? So first one is primitive recursion, right? I wish I could, you know what, I'm gonna bring both of them up side by side. It's just much easier to think that way. How do I do it? This. Oh, no, that won't bring it up side by side. I
Thank you.
drag it out.
Thanks.
No problem. Yeah, sorry we didn't get further. I know some people have time constraints. Right, this is not a PC. It's a right click? Is right clicking even a thing? Okay. They still only have one button on Mac mice. Should they finally cave and put a second button?
I think mine has 2 buttons.
Finally. You can tell I love Macs. Okay, let's bring everything up by side. Looks much better. Good. Duplicating the emphasis in the read write head. Okay, so how can we essentially mirror what you can do with like primitive recursion via a Turing machine? So what's your input? Your input is going to be a number and your input x1 through xn, right? And we want to go from that to some output.
So, at the very outset, are we trying to transform some number x1 through xn into g of n, h of the bottom
You
right?
are given, essentially, you're at the n plus 1 x1 through xn place.
Okay.
Like you
okay,
have an input, and
okay.
you want to do the primitive recursion.
So we don't need to bother with the first line.
Well,
Is it-
because think about, look at composition, for example.
Mhm.
If we look at composition, you have h of x1 through xn, and you want to compute the right side.
Right. Right.
Right?
Right.
That's really what's happening here too.
Right.
You have h of some number and x1 through xn,
Right.
and you want to compute whatever the primitive recursion should equal,
Right.
which how primitive recursion is defined is recursive, right?
Mhm.
So if you have h of 6 and then your input, then the number it equals is based on h of 5 of some input, which is based on h of 4
Sure,
some
right,
input, and
goes
so
all
you're
the
going
way
to have to do all those computations
Right.
with the Turing machine.
Right.
Does that make sense?
Mhm.
Cool. So yeah, any thoughts? I can start writing stuff down.
It seems like we need to do some kind of like input duplication, like the composition.
That sounds promising. Oh, we already are using, this is reserved, right? Because it's x1 through xn. I think, so I'll call this m. So this is on the tape. To start. Okay, so you want to do some input duplication, right? So if you want to do input duplication, are we duplicating the m? Let's just try stuff.
Don't you want to duplicate the x1 to xn?
Okay. So now we would have m. I don't want to keep. I'm gonna just like write this as squiggly x. It's a terrible squiggly x. What's the best way to write it? That work? I don't know. Whatever. I'll just keep writing the whole string. Give up. x1, xn, x1, xn. Okay, so we have this.
Do you need to put a blank in between or?
Yeah.
Okay.
It's always safe. It's always easier to do it that way. Cool. What do we do with it?
How do you alter the m?
We want
Right.
to get to n minus 1,
Yeah.
right? But what if m is 0? That's
It's a good question. What do you do when m is 0?
it's defined as just f of x.
Yes, you compute f.
Right.
So in
Oh.
the simplest case, if m is 0, this copy is kind of unnecessary. If m is 0, you should just compute f. You can delete this and compute f of this.
We
So don't
delete
you
m.
want to just start by checking if m is 0? You don't even have to do any.
So check what m is. It's definitely it's definitely an important first step. Okay, if it's 0, we know what to do, right? You can delete m, and then you can compute f on what's left. Kind of like how they delete the input when they're for the function composition. They like delete this excess knowledge and just do what they need to do. Okay, so that's good. It's a good start. What about for greater numbers? What if m is 1? Or 2? Let's do 2. Now what? I don't like this. It's close, but I think we need to do a little more. Let's keep that blank. But think about it like this. How many times do I have to compute this function? So when it was 0, how many functions did I compute in some sense? Some
One.
vague sense. 1. Yeah, I computed f. If m is 1, how many recursion levels are there? There's only one level of recursion, and then you compute f, right? So for m equals 2, how many inputs do we think we'll need by the end?
3?
So you'll want 3
what is
copies.
G exactly?
Is G in this one?
Yeah, that's
In
what.
primitive recursion?
Yeah.
Oh, G is the recursion. So like, you can think of it like this. Let's say I wanted like f of, so let me use, F's fine. Let's say I define some primitive recursive function that such that f of x, f of x equals 2x, g of x equals x plus 1. And now I'm going to define h based on these. Okay, so let's see what happens with h. This should give us a feel for what primitive recursion is actually doing. If I take of 2 and then, so this is the number of times I'm recursing, and then I put in 3, well, what happens? H of 2, 3 is equal to h of 1 g of 3, right? Is that right? Just by the definition of primitive recursion?
Because in here he says it would be like G of 1, H of 1, 3.
Give me a sec.
I think.
Let me double check that I'm remembering primitive recursion, right? Yeah. Oh, right, and then you put the input back in, I guess.
How come G is on the outside?
When you put so you take this. Oh, sorry. Yeah, my bad. So it's the number of times you do G on that. Got it. Sorry, I have it backwards. My bad. You're right. Sorry. G of H of this, and then let's put the original input back in too.
And then in his definition, it's like.
What's it now? So this equals, I'm going to go down now because otherwise it's gonna go off camera. Now it's G of
Should be h of 1.
Yeah.
yeah. Sorry.
How come it's not inside h of 1 comma 3 and then comma 3?
Is it comma 3? Yeah, it is comma 3.
No, this is right. Right.
To add
So
to this,
G of n, h of n.
This is how he writes it.
Like, so I get the G of 1 because n is 1, right? In this case,
Oh right, so this has to be
1
1
h
comma
of
3.
1
yeah,
comma
my
3.
bad. This is what I'm messing up. You're totally right. 1, comma. Yeah, the way I've seen this before is
Comma.
slightly
And
different
then comma
notation.
3, I think.
And then
'Cause
comma
that's
Yeah.
the 3
3,
Yes, three
because that's
is
the
the-
original input.
original input.
And then we have G of 1 of G of 0 of H of 0 of 3 of 3. Nope, not quite. Sorry.
There's another 3.
There needs to be another 3 there.
Yeah.
isn't the h a one place relation in the box that you on the, to the left? But now it's taking in lots and lots of inputs.
G is an n plus 2 relation.
Oh, so it changes every time you.
No, G only has 3 inputs. Look, this G has 3 inputs. This tree has 3 inputs.
What about the G under the F?
What?
Right
This-
to the left.
This G? Look, it has 3 inputs.
left. In the box that you, like in the box. Like move like a foot. Yeah, that one. Yeah, that's just G of X. That's just X is just one input there.
Oh, yeah, sorry. Yeah, that's bad.
Because, yeah, I'm having trouble understanding this. I don't know what G is. Like, it's not shown.
Yeah. No,
I
G
think
can
it
be,
just
so
says
the
any
reason for that is
plus
because G
2.
can be defined with respects to the step, but I'm going to have it ignore its step input. Or actually, let's make it more fun.
G has to have 3 inputs.
Let's see, G
Which is
I'm
insane.
just going to call them ABC because I don't want to think, I
Yeah.
can't remember which variables I've used. And what that would be is, actually make this one X, I guess. So let's ignore C because that's too complicated. I don't want to deal with that. And let's do it as X plus A. Okay, what about this one? Now H is easy, right? I can stop doing that.
F of 3.
Yes. Okay. So the important thing is F is generally something is fairly simple, but G can be very complicated. G can be based on the number of recursions you've done, right? The level of recursion you're at, and it can be based on the original input, and it can be based on what's come up from the other level of recursion. So, which all makes sense. Like these are all 3 pieces of information you have. You don't necessarily use them all. So in this case, I compute this. That's easy, right? So we have 6. So we have G of 0 of 3. And it ignores the 3 because I ignore the original input in this particular definition of G. I add the level of recursion I'm at to X, and then I'm done. So for this one, it's just 6, right? Because the level of recursion was 0. Now we have G of going to the outer one of this of 3, which is what?
7, right?
7. That's it.
Okay.
But you can see how general this is, and it's super useful because you can do really just like any recursion with this based on the number of times you've recursed, the original input, and what has happened at the previous level of recursion in terms of computation. That is primitive recursion in all its glory. So how can we deal with that there? I'm going to erase all this, if that's okay. Or do people like this? I don't know. I'll leave it for a sec. What's our idea for this, though? So what information does G need again?
It needs to get M minus 1.
It does need m minus 1. So if I wanted to, I'm like warring with, I'm gonna erase the top one.
It also needs the original set of x's, right? Or the original arguments.
Okay, so we can copy m minus 1 here, right? So we have, and the original input, right?
Mm-hmm.
We need that still. And it needs what happened at the earlier level of recursion. Where do we get that though? We get it from the next copy over. So in this case this equals 1. So now what would happen here?
You get F of those things.
Yep.
Is that off camera?
Almost. Bring it down a bit. Okay, so better idea. Do equals 0 over here. And this whole thing is f of x1. Right? Okay, what information will this level of recursion need? What do we need to compute G? Because that's the next thing we want to compute. What 3 pieces of information, and do we have all of them?
Yeah, we need m f of x1 to xn, which
We don't want m. We want
or n minus
yeah.
1.
We want m minus 1, which we have,
Mm-hmm.
because it's the level of recursion you're at. And then
the f of x1 to xn, because that was the h inside,
yes, exactly.
and then the copy of the input.
Yep. This is our a, right? If we look at it as like a, b, c, for example, or in this, I guess a, x, c. This is our x. This is our a, and this is our c.
So they're out of order.
Doesn't matter.
Right.
Right. But we have them all, and we can take all of these and then do what? Compute the.
H or
We compute h of 1.
right.
Yes. So h of 1, whatever our input was. So now, with all of this, I'm going to start erasing more stuff. Sorry. But I need more. I can't go up anymore. And this is more important. Let's get rid of this up here. Equals 0. And then, so this gave us f of x1 through xn. And this is h of 1 of x1 through x. Right? And then do we have all the information we need here to do G? So this is the entire argument, basically.
Right. Right. And we can and m could be anything. So it's just do the same deal and then you get to the last step and it's 0 when
Once
you
m is
F,
0,
and then you
yeah.
go all the way
So
back.
check m. If it's not 0, copy m minus 1, one blank over from what you already have written down. Then copy your input from over there to here. Then check m.
Right.
Rinse, repeat.
Wait.
Does that make sense? Question?
How do you
What's the-
factor in G?
What's the what?
It's a similar question. Like, what's the point of turning that into h and going away from g? Do we know how to compute g or not?
Because each G, yes, but G of, what are we trying to compute overall? we're trying to compute h. Our goal. I spoke that. Can't spell anything. Luckily, math doesn't require much spelling. I've realized. I was a goalie for like 10 years, by the way. It was even sadder than it looked. Trust your. There you go. So yeah, that's our goal, right? That was what our input was. So we're going to need to compute g to get this. But g takes three things as input. This, and the previous level. Right?
Again, not in that order, but it doesn't matter.
But not in that order, but it doesn't matter.
Right.
So right?
Oh, I got it. Okay, cool.
Right, see look, within g, h is defined with respect to g, so we're going to compute g at each step. But our result from computing g is an h. Right, and we feed that into our next computation of g. Does that make sense? So the last thing we do to get h2 of the input of x1 through xn is to compute g of this, and this.
So
And
G
that is
of,
equal to this by definition.
so can you say that one more time?
So let's go from the first one even, okay? To get h1 of x1 through xn, it's defined as g of this, and this in that order, right? Yeah. Okay.
But isn't the n and g one less than the one in h?
It is.
But the left-hand side h. On the right-hand side, the h of n is the n is the same. G of n, h of n.
This is h of 0.
Yep.
So the h we get out from our computation when we use g is h1.
Okay.
Does that make sense?
Mhm.
That's why it is one greater. Here too, we compute h2 of x1 through xn by current level of recursion, previous h, which is h1 here, right? And our original input. Does that make sense?
Oh, so it's g1 of h1 of whatever.
G doesn't have G has the same number as, I guess, it's gonna be G of 2 of h1 and x1 through xn and x1 through xn.
Because the way he writes it is it's
But notice- 'cause-
gn.
Right. It has Gn is this, so G of n.
But like it would have to be 2 of 2 and then the h.
Oh, I see what you're saying.
Yeah.
G of n.
And the n is the same n as
Yeah,
the one in
it's
the
the
h.
same as the one in the H, which is true. So you use this.
Yeah, I'm not sure why you go back to h1. Why can't you just?
It doesn't matter,
Okay.
honestly, because what you can do is you could just if I have this piece of information
Mhm.
and this, I can just take this minus 1 in my
Okay,
computation of
yeah.
G. You're right, though. Good call. Does that make sense?
Yeah. So is the game here to get what's on the tape, namely x1 blah 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 to xn, to get that into the form so that G on your right hand side of right there, the right hand side of G can eat it?
The game, I'm not 100% sure what you were asking. The game is to get from this input
Right.
to h of m of this.
And so
That's it.
right. So the way we do this is we copy things, we move things around, we subtract 1, and we do this. Oh, okay, right. I see what you're saying. Right.
You do m plus 1 times.
Yes.
Writing it at the same level that he writes composition shouldn't be that bad.
Mhm.
Doing this all out in terms of a straight Turing definition would be hell. But yeah, as you guys know from previous homework, if you tried that. But let's see. Cool. Should we talk about minimization for a bit with the little time we have left? Does this hopefully make? Do your whole objective in general more clear though too. Like I know we only
Yeah.
talked about primitive recursion, but like
I think minimization is a little bit easier than this.
it might be actually. I hadn't really thought about it much. Oh right, because you just keep a counter.
Yeah. Yeah, you
Think
just
it
keep a
is easy.
counter and then you return the counter once it equals 0. The f of whatever.
Sounds right. Does anyone else have any objections to that?
Can you explain what a counter is? I mean, I guess like.
Just keep a sequence of like ones that is equal to the number of steps you've taken.
So like every time you do something, run to the end and put a 1 down.
Basically, yeah. So we're trying to output a number of ones equal to I, right?
Mhm.
We're given some x1 through xn, and we want to output the first I, for which f of I of whatever equals 0. Is that right?
That sounds right.
Sounds right to me. That requires primitive recursion, right? But I mean, we already did primitive recursion, so you could just say compute it because we did it. We've done everything else. So yeah, we compute f of 0 of x1 through n. If it equals 0, we're done. If not, we increment the counter to 1, and then we compute f of 1 of x1 through xn.
Wait, so do all of these numbers have to be represented by ones?
I think we're using unary right now.
Or can we just say that we write this number to the tape? Like a blank and then this number and then
I think
a
you
blank.
can honestly just say keep a counter.
Okay.
I don't think anyone's gonna give you a hard time. Where you keep it might matter a little bit, because presumably we want the number. Presumably we want to output the number at some point. So I would say like, you want to, if your input is written right here. Then I think your best bet is you want the counter right here. You want your output here, just like starting where the input started.
It's like before the input?
It's probably the best place to keep it, to the left of the input.
Like I was thinking like blank, counter, blank. Input.
I would, or just like, we know now, because he says earlier, right, that you can work rightmost only. You can have like infinite workspace to the right, and just have a Turing machine work on the right side, and that's just as powerful as one that's infinite in both directions. So one of the easy ways to do it is just to keep a counter to the left side of your tape. Other way to do it is tricky way to do two tape Turing machines. Certainly you can change the alphabet. Another trick you can do is you can only do your computation entirely on the odd numbered cells, and then keep your counter on the even number cells. Right? You can in fact have like any finite number of tapes this way on one tape. The only additional power you gain from having multiple tapes is your read-write heads on each tape might be in different places on each tape, and might move in different directions. But this is like an equivalent way to essentially have like a head that is basically like if it moves right on one tape, it moves right on all the tapes. So one way to do it was like we did last time, where we changed the alphabet and stacked multiple symbols in a single cell. Another way to do it is to just space the cells.
Okay.
There's like a billion ways to keep counters. But yeah, so I would say the easiest is just keep it left of the input with a blank in between, and then do all your work on the right side of that, and then go back and retrieve it and put it where the input was. Does that make sense?
Mhm.
Like, one sec. I'm just gonna draw a diagram. Input. Blank.
Wait, this is for minimization, right?
Yep.
Yeah, okay.
And then we're gonna just like make a counter over here. Have our blank calculation. And then at the end, move this back so that we have blank counter. Right? Something like that. Or I guess in his definition there's always a blank at the beginning, so I can just kind of remove that. guys get the idea. Does anybody have any other questions or concerns about the minimization one or about write-up or details? I'm still gonna have to post that detail about it might not be defined on certain inputs.
Well, it said-
but just ignore that for now.
It said it's defined for all j is less than I, so you can
Sure.
assume it halts on I, right? So like we never would go past
But
I.
what do you do when you hit the one that is not defined on? Like if you how you're just running through and blindly calculating f of I of something. And so
I
when
see.
f of I isn't when f of I of something isn't defined, what does your Turing machine do?
Well, it says
That's a
f-
little confusing. To me.
Well, it says it's defined for all j is less than I, and then he defines f of I equal to 0.
Defined for all. Sure, but what if it's not defined on some input? What is G? Is G just not defined? And what do you output?
I mean, like I would start with
What
I
is what
equals
if F
0.
is not defined anywhere? Let's just say like F is this terrible function that isn't defined at any point. It's just nothing. What do you do on the first calculation? It doesn't equal 0. And nothing else is defined. Like, is G of X then just not defined? That's kind of what I would assume. I don't know. It's very unclear to me. It's
Okay.
all just like some definitional mess that I'll dig through without you guys having to waste your time on it.
Okay.
It's one of those corner cases that I could give you what I think is the answer, but I also might just be wrong until I look at a bunch of definitions. Yeah. But I will try and make that very very clear Piazza post about that. I think with everything else though, it should just be whatever. I mean, sure, like F might not halt. I mean, G might not halt. But that would only be if this doesn't. So, if I'm wrong on that, I'll also include that in the Piazza post. I'll ask him, but I'm pretty sure. I mean, he seems pretty clear in his lecture notes too. That the minimization might not halt. Right, like he even when he's talking about the for loop, he's like the for loop gets a number beforehand and like knows when to stop. The while loop might not. And he even says later that like if you define something with the first 5, it'll always be total, which means you can always compute the answer. But the other ones,
So this makes sense. I'm still confused about this dot syntax. What does that mean?
the dot where at the
Like,
end of
in the
I,
equation. Yeah,
I think that's just a period.
that's period. Okay.
I think so. Yeah. Is it? I have no idea. I'm not sure. I can try and clarify that in my post too.
So the way I now
Some of the notation and minimization is throwing me off a bit, but for the most part, I think we understand it. What were you saying?
I was just gonna say I think I'm reading it as G blah blah, blah equals mu I, i.e. it just equals the lowest I such that whatever, and then
That's
then
kind
new
of
sentence, and
that's
then
kind of what I'm reading it as too. Am I the only one? I'm not the only one who finds this weirdly written, right? Like, I think it's just a little hard to parse, but because that's not the typical notation for something like that. But maybe it is. Honestly, there's so many like different standard notations for things mathematical that. Did I tell you guys about the horror story of this textbook I read with that used dot notation? Awful.
thought notation.
Dot notation. They decided that parentheses were a terrible idea, and that we should get rid of parentheses.
That sounds
It's
like a
this-
terrible idea.
It is a terrible idea. Parentheses are great, and you shouldn't. So yeah, that whole book doesn't have parentheses in it. Uses this weird dot notation to tell you priority of binary operators. It was a good 600 pages. I enjoyed it thoroughly. It was awful. Cool. Hopefully, yeah. So, you had a question on something else, right?
Oh,
Let me
okay.
stop this. And I can. Yeah, I'm not that much over. I can take a bit more time.
It shouldn't take more than 5 minutes.